In the last video, we figured out how to solve for a K value. We're going to do the opposite in this video. We're going to be given the K, the equilibrium constant, and we're going to be asked to solve for equilibrium concentrations or pressures. And to do that, we're going to have to use our ice or rice table as we did before. So let's jump right on into this. So as is always the case, they're going to have some sort of equation that they're going to give you. In this case, they give us this equation right here, and it is not balanced. Typically, but in this case it accidentally balances off as a 1-to-1-to-1 ratio. They also should probably give us the states of matter, but they don't. So what I'm going to do is I'm just going to jot this down below again, this equation, and I'm going to work on our little ice table. So I'm going to set it up here as PCl3 and I'm going to make my ice table next to it. ICE. Initially, they give us for PCl5, they give us 1.00 molar of this, and they give us 0 and 0 of these two things. Now, because of that, and we always need to figure out which direction the reaction is going to shift, we would normally have to solve for our Q. But in this case, again, there is nothing on the left-hand side. So the only possible way that we can go in this case, isn't it, to the left? And we're going to go to the left. Now, what that means then is that we're going to lose x here, and we're going to gain x here and here. And at the end, in our equilibrium, we're going to end up with x here, and 1.00 minus x here. Now, I kind of broke my own rule, because whenever I'm setting up problems like this, I always like to set my k up to begin with. And I'm going to write my k expression right here, right now. And that be k is equal to my products, concentrations, raised to their coefficients all over my reactant concentrations, raised to their exponents. And if we actually plug the numbers in, we end up with 1.00. These are our equilibrium values. So these are the ones that we're plugging into our equation right here. Minus x on the top, all over x times x. And that's going to be equal to the value they gave for us for the K in this problem, which happened to be 16, equals 16.0. Now, I don't know if you're familiar with these types of problems. I'm guessing you are, because you've taken math before. But if you set it up and you actually rearrange the equation, you're going to end up with this. I'll let the involuntary chill go through your body. In other words, in order to solve for this, you're going to have to use the quadratic formula. Now, I know that some of you guys have learned the song for the quadratic formula. It used to be a beast for us, but now you can just plug it into your calculator, and in case you don't have your calculator like I don't, you can go to a site like this, and what we can do is we can just plug in the values for each of these. I'm going to plug in 16 here, 0, and minus 1. Now, if you take a look here, it'll give us two possible roots, two possible solves, 0.25 and negative 0.25. Now here's the problem. Can you have a negative concentration? To that I would say no, you cannot. So therefore, when I go back to my original problem here, I'm going to end up saying that my x then needs to be 0.25. Now, what does that mean? Just saying x is equals 0.25 mean like dropping the pen and being going like, yeah, I'm done here, is not good enough. What you can do is this. Isn't your x equal to 0.25? Isn't that also equal to your PCl3 concentration? And isn't it also equal to your Cl2 concentration? So we know this because we see here the x value here and the x value here. These are our equilibrium values. Now, the only one that's going to be slightly different is this one right here. And see how we have the x is right here being subtracted from the 1.00? And if we did that, 1.00 subtract 0.25, wouldn't that give us a value then for our PCl5 of 1.00 minus 0.25, which would give us 0.75. These are all concentrations in molarity equal to these, and these would be our three equilibrium concentrations. Yeah? Now, Let's try one on your own here. And I'm going to give you a second here. I'm going to have you guys pause and solve this all the way out, and then I'll jump back in with you. Okay, now if we set this up, there's only two things here, right? We have N2O4 and 2NO2, and if you take a look at this, I'm pretty sure that that's balanced. 2 N's, 4 O's, and 2 times 2 is 4 O's. So I'm going to write this into our expression right here. I'm going to go N2 I'm going to write this expression here. I'm going to write N2O4 and our double arrows, which look terrible, 2NO2 right here. Our initial concentration, they say, is we start with 0.115 molar of this. 0.115 molar of this. Yeah? And we have 0 of this. So what's our change going to be? Well, aren't we going to lose x here, and aren't we going to gain 2x here? And when we're done, our equilibrium is going to be 0.115 minus x, and I'm sorry if I write it plus 2x here. And then over here, when we have a 2x, if we plug it back into our expression, k, and this is a c because we're dealing with concentrations, right? Wouldn't it be equal to, and again, I should have done this first, but I'm going to write NO2 squared all over N2O4. And we want to get in the habit of doing this prior to doing any of our problems. So on the top here, our NO2, we're going to have 2x, and that's going to be squared. And then on the bottom, we're going to have 0.115 minus x, and all that's going to be equal to 0.36. All right, so if we have this right here, then we can rearrange this if we want to get to 4x squared plus 0.3x minus 0.0414. And these are our values we're going to plug into our calculator, our quadratic formula calculator, which I'm going to click on yet again. And we get two choices here. We get 0.15624 and we get 0.0662. Again, we can't have a negative value on that, so we're going to go with 0.0662 is our x value. Oh, my cat decided to join the fun. Now, what does that actually mean? We have to then, in all of our problems, we can't just say x is equal to and be done with it. But if you take a look up here, isn't our NO2 equal to 2x? So we'd have to then go, all right, that's equal to 2x, right? So that'd be 2 times 0.0662 for our concentration of our NO2. My cat's all over the place, and I'm going to plug that into my calculator, aka my phone. And that gives us 0.1324. And on the other end, for our concentration of N2O4, it's 0.115 minus x. And in this case, our x value again is going to be 0.1 okay, minus 0.0662, and that's going to give us 0.0488 molar. That's going to be our concentration at equilibrium of our N2O4 concentration. Now, lastly, and I didn't do this here, but they ask you in the problem to solve for Kp. I'm just going to set this up for you because my calculator clearly is not with me. But isn't Kp always equal to Kc RT change in N? The Kc we're going to use right here is going to be from this. The R is 0.08 0.0821, or 206 times the temperature. Now remember, this is not in Kelvin. It has to become Kelvin, so don't we have to add 273 to that? So that would be 373 Kelvin. And then the tricky part of this is that we're going to have to figure out change in N, and that's always our products, number of moles of gas, minus our reactants. So we have 2 here, and we have 1 here. What's 2 subtract 1? Yeah, it's 1, right? So in this case, we're going to take all this to the 1 times our Kc, and that'll give us our Kp value. Now, in the next video, I'm going to show you how to do it the short way. And typically we'll be able to do these problems only when we have our K value that's really, really small. And when I say really small, how do we know what really small looks like? Well, whenever you have times 10 to the negative 4 or lower, typically, here we have times 10 to the negative 9 if you take a look at the problem, we can make a couple of assumptions that avoid us having to write these really long, really complicated polynomial problems, although the quadratic formula is not that difficult. So let's try this problem here, and we're going to do an ICE problem just like we've done before. We're going to do an ICE. The equation is balanced off already, so we don't have to worry about that. And we're going to initially have 1.00 atmospheres. This is actually a pressure problem. And we're going to have 0 and 0, both of these. Since this is a 1-to-1-to-1 ratio, whatever we lose here, we're going to gain here and here. So we're going to lose x here, we're going to gain x here, and we're going to gain x here. At the end, we're going to have 1.00 minus x, and we'll have x and x. So if we wrote our Kp expression, our Kp expression looks a little bit differently because we would do P, and then whatever our substance is, we write it as a subscript. So we write, since our products are CO, and it's raised to the 1, times the pressure of Cl2 raised to the 1, all of that's going to be over the pressure of CoCl2 raised to the 1. And so if there had been coefficients, we would have raised it to 2, etc. So when we plug the values in, and we know our Kp value is 6.8 times 10 to the negative 9, we can then write this on the top. When we have, taking our CO and our Cl2, we'd have x times x, and on the bottom we'd have 1.00 minus x. Now, here's the beauty of this. We're going to do something called the 5% rule. And I've heard it said sometimes as like the fly on the elephant rule, but if you take a look at this x right here, this is how much is lost from this 1.00. And if you take a look at our K value, what this essentially says is that the amount that shifts over to this side is essentially a billionth of what was here originally. So if you took a look at the comparison of the two sides, remember, it's always products over reactions. Essentially, we have 1 billion times more reactant than we do product based on this coefficient, because remember, our product's on the bottom. What it essentially says is that we lose very, very little. So, for example, if I'm like a billionaire and I lose $1, that doesn't make any difference to me. So what I can do then is I can get rid of this x and call it the 5% rule, because 1 minus this very, very small number is so tiny that we can assume that it doesn't really impact our problem. So we can go like this in our problem and write 5% rule. My students in the past have said we talk about dead frogging it as the 5% rule because it kind of looks like 2 dead eyes and a tongue going out. But if we now want to solve this problem, it makes it a lot easier, because we can go like this. We go on the top, we have x squared. On the bottom, we have 1.00, right? And on this side, we have 6.8 times 10 to the negative 9. Now, sometimes students say this, well, wait a second. You said that we could get rid of this x. Why didn't we get rid of this x and this x? Because take a look at what we started with. Didn't we start with 0, both of these? If I start with 0, you can't take away anything, or sorry, you can't add in something and say that that is not doesn't matter to me. So giving me x when I have nothing matters. I can't get rid of that x. It's like if you have 0 money and someone gives you a $5 bill, you're not going to dismiss it. So in this case right here, I cannot get rid of these two x's, and when I solve 1 times this, wouldn't that be 6.8 times 10 to the negative 9 equals x? And if we want to solve for x by itself, don't have to take the square root of both sides. In this case, our value is going to end up being, it's going to give us 8.25 times 10 to the negative 5 equals our x. Which, if you take a look back, it matters what x means. So isn't our x going to be equal to the concentration of CO and the concentration of Cl2 at equilibrium? And if we do the math on this, wouldn't we say that our concentration of CoCl2, wouldn't it be 1 subtract, and let me do the math here, 0.000825. If you subtract this from 1, isn't this essentially going to give you just 1? Now, one of the things we have to do, and you see it says, what is the percent of CoCl2 that reacts? The reason I ask that is because we often want to prove our 5% rule. Because the only way we can say that this x right here doesn't matter is if this value right here is less than 5% of this value right here. And again, we picked some kind of easy numbers to work with here, but couldn't I just go like this and go 0.0008205? And in case you're wondering, that is the same thing as this. Divided by 1 times 100. Wouldn't that give us a percentage? And if you want to slide the decimal places over, if we divide by 1, wouldn't that then give us, and then times 100, wouldn't that give us 0.00825%? If you lose 0.00825% of yourself, that's not very much. So this is actually a pretty good assumption that the x doesn't really matter. And of course, we're going to practice a bunch of these problems as we're going through them. Hopefully this has been helpful. I'll see you in class.